Okay, so this is another segment. This is a soil fertility and plant nutrition segment. Again, these will be on the website. They're probably up there now. We're going to cover three main things. Oh, my pointer. We're going to cover plant nutrition. We're going to look at a functional soil model. I like to call that beyond the pie chart. And we're also going to look at some soil chemical properties that relate to soil fertility. Okay, so we'll probably get through the plant nutrition before lunch. So, plant nutrition topics. We're going to talk about growth factors, plant nutrients, mechanisms for nutrient delivery, and the law of the minimum, and we'll start first on growth factors. Okay? Now, we're focusing a lot on nutrients in our perspective, but the fact is that plants need a number of things to grow. They need enough water. They need oxygen in the root zone. They need enough temperature or heat for their ecological adaptation. They need carbon dioxide for photosynthesis. They need mechanical support, and they need nutrients. So I like to bring this up because a lot of times when we're troubleshooting and trying to figure out why a crop isn't doing well in a certain place, we get a little too narrowly focused if our orientation is nutrients, and we fail to realize the fact that there are other things that could be limiting also. As a matter of fact, a lot of summers, water is what's limiting our growth, right? If we have a period of time where we go without water. Nutrients is just one of the growth factors. And let's talk about what a nutrient is, and this is a definition for plant nutrients. It's an element, that means you can find it on the periodic table, that has a direct effect on growth or metabolism in a plant, right? It's required to complete both the vegetative and reproductive stages of life, right? And it needs to be specifically required. It can't be substituted by something else. And these criteria, as the system we use to define nutrients, was pretty much set up by the 1950s. Initially, when people started analyzing plants and realizing that some things were essential, there was a misconception that just because it was in a plant, the plant needed it. Of course, plants can take up things they don't need. So the plant physiologists decided that this in fact is the set of criteria that must occur in order for something to be considered a nutrient. You can pick up different plant nutrition books and find differences in terms of what's essential, and a lot of it right now comes down to, is it essential for higher plants, or is it essential for algae? You know, is it essential for all species or essential for all species? So I'd like to tell you there's universal agreement on what is and isn't a plant nutrient, but that's not the case. So you have a table in Mid-Atlantic Nutrient Management Handbook is what I use as the abbreviation for that book you have on disk. On page 56, table 4.2, you have this table. Ooh, look, I need a little more space there. Anyway, there's non-mineral nutrients, and that means plants don't get it from the soil. Okay? Then there's mineral nutrients. That means the plants do get it from the soil. So let's look at this list first, carbon, oxygen, hydrogen. Where do plants get their carbon? They don't get it from the soil. Atmosphere, okay? They split carbon dioxide and photosynthesis. How about the oxygen and the hydrogen? Where do they get that? They split water during photosynthesis, and that's the source of the oxygen and the hydrogen. So those things are non-mineral nutrients. They do not get it from soil. If you pick up a plant nutrition text, it'll talk about these. If you pick up a mineral nutrition text, it'll ignore these entirely because they're not from the soil. In terms of mineral nutrients, we have some terminology you're going to want to be familiar with. We have nutrients called macronutrients. That means they're needed in relatively large amounts, typically expressed as percent on a dry matter basis. We have micronutrients, things that are needed in smaller amounts. Not that they're less needed, we just don't need as much of them. These typically are expressed in parts per million. Okay. Among the macros, there's often a distinction between the primary nutrients, nitrogen, phosphorus, and potassium, and the secondary nutrients, calcium and magnesium and sulfur. So I would be familiar with the categories and the terminology that relates to this, and we're going to have a little question on that a little bit later. In terms of understanding how nutrients behave, it's important for us to know a little bit about their chemistry. So we'll be using the term cation. A cation means that it's a positively charged ion. An anion means that it's a negatively charged anion. Some nutrients are cations, some nutrients are anions. You'll see that others have both forms. And then some are actually neutral. That means they exist in a form where there is no charge. They're chemically, electrically neutral. This too is in the Mid-Atlantic Nutrient Management Handbook. It's table 4.1. And on the left-hand side are a bunch of nutrients and the form in which they exist. And you see that I organize them according to whether or not they are cations, or on the right, anions, or in one case uncharged. So if you look at nitrogen, you can see that nitrogen exists as cationic form called ammonium, NH4+1, or nitrate, NO3 -1. Okay, nitrate can actually exist in either the cationic or the anionic form. Dr. McGrath will talk to you about the process whereby ammonium is transformed into nitrate this afternoon. Potassium, calcium, and magnesium, some are +2. These are divalent cations, whereas potassium is 1. A lot of our micronutrient metals are down here. Okay, iron, zinc, manganese, copper, cobalt, zinc. These are called micronutrient metals. Metals because of their characteristics, where they are in the periodic table. You can see that some have more than one charge possible. Both iron and manganese have an oxidized form and a reduced form. In a well-aerated soil, they're going to take on the higher valence, iron +3, manganese +4. But if that soil becomes anaerobic, reduced conditions, flooded for a long period of time, they actually change form from iron +3 to iron +2, from manganese +4 to manganese +2. Okay. Anions, nitrate, of course, it's a small oxyanion. Phosphate is much larger. Sulfate, chlorine, just by itself. Chloride, borate. Boron can exist in a number of forms. 2 of them have charges. Undissociated boric acid is neutral. It has no charge. Molybdate also. Some of these big oxyanions, phosphate, molybdate, sulfate, borate, they tend to behave similarly. Just like the micronutrient metals, we can make some general statements as to how they behave in the soil. Micronutrient metals tend to have a pretty strong association with soil organic matter, with humus. The large oxyanions like phosphate, molybdate, borate, sulfate tend to have a strong affinity for the iron oxides in soil. So if we know what form in which something exists, we can make some generalized statements as to how they're going to behave. Or if we know how one of a group behaves, we might be able to generalize it to another thing that's chemically similar. So in terms of plant nutrient terminology, I'd be familiar with these. I'd be able to identify mineral nutrients from a list, non-mineral nutrients, macronutrients, primary nutrients, secondary nutrients, micronutrients. That's thrown at you. Be sure you can tell them apart. Remember, this is a multiple choice exam, so it's a matter of recognizing the correct answer, not recalling it, which always makes things a little bit. So let's talk about the relationship between plant growth and nutrient concentration. For example, what happens if a nutrient doesn't exist in an adequate supply? Okay, can a concentration of a nutrient be too high? What do you think? Can you have too much of something? Sure. Can in our nutrition, and you can in plant nutrition too. Here's a very nice diagram I like that shows the relationship between relative growth, where this is 100% of relative growth across the top, and this is some essential element. Let's look at one at a time. We have a very low concentration, a low, an intermediate, a high, and a very high. And you can see that if your concentration of that nutrient in the plant drops too small, you can have some pretty severe yield reductions to practically nothing. In the optimal range, you have a wide range where increasing the amount of nutrient in the plant tissue doesn't cause an increase in growth. You've already maxed out its growth potential. But if you increase the concentration even higher, you can actually get some toxicity, some suppression of growth due to too much of that nutrient in the soil. I will tell you, quite frankly, that I've never seen anything about toxicity for the macronutrients, but it is something that's documented in a number of cases in both practice and the literature for micronutrients. It tends to be a much greater sensitivity to overdoing micronutrients than the macros. And actually there was some new work published in the last Soil Science Site of America that showed that there's some additive effects. Like if you have almost too much calcium and almost too much zinc, but they both exist at the same time. It's like adding them together. There's an additive negative effect. How can you tell if a nutrient is deficient? Well, you can look at your plant, and one thing you're going to want to do is know the major nutrient deficiencies, because that, again, is fair game for the exam. I'll give you a reference here in a minute. This is from an Ontario bulletin, but when you start looking at plants and thinking, could it be a deficiency, could it not, remember that there's some terminology that we're going to run into when you read a key or read someone's description. First of all, these problems don't all look the same, do they? Okay. Sometimes there are color changes, for example. This is death or browning, whereas this is red. Sometimes it's at the edge of a leaf, as this is. Sometimes it's the area between veins, interveinal. Okay. Sometimes it's spotty. Okay. So you're going to come across a whole vocabulary where people communicate about nutrient deficiencies. So be sure that you know where it occurs on the plant. For example, is it the new growth? Is it the old growth? That's important. Where on the leaf is it? What does it look like? Is it a certain color? Is it alive still, or is it dead? Okay. All kinds of variations in terms of what we see out there. And it often differs across crops, too. Some of the micronutrient deficiencies in particular look different in different crops. I will tell you that, and this is linked on our website, the Mid-Atlantic Water Quality website has PowerPoint presentations for every chapter in your handbook, and in Chapter 4 they have a detailed description of nutrient deficiencies for major crops. So I would spend some time looking at that. I do want to tell you that if you can see a deficiency, you've got a real problem. You've got a real bad problem. All right? We'd like to be able to know. We'd like to be able to know what a potential problem is and solve it before we plant the crop. Okay? Visual symptoms usually indicate a very severe deficiency situation. Another way you can tell how your plants are doing is using plant analysis. And in that case, it's really important to collect the correct plant part at the correct time. We've got a really good bulletin. Unfortunately, it's out of print right now, but it's on our website called Plant Tissue Analysis that runs you through kind of the ideas behind plant analysis and points out some of the problems with using it. Many producers of high-value crops in this country use plant analysis as kind of a routine thing along with soil analysis, but it's often used in a troubleshooting mode. You know, part of that field isn't doing well, is it nutrient related, and someone will go out and take some plant tissue samples from there and try to see what's going on. Okay. Remember I told you that if you can see it, it's usually pretty severe. Most people agree now that if you actually have a nutrient deficiency that's obvious to you from symptoms, you're already down in the pretty severe range, okay, down in here. But there's a region in here that's often called hidden hunger, where you're sustaining a fairly big hit in terms of yield reduction, but you can't see anything yet. Plant still looks normal. So realize that if you're seeing it, you probably cut your potential to 50% or more. And most people agree that with an annual crop, trying to fix it in that season isn't going to pay off. Okay? You need to make sure you don't make the same mistake again. Hidden hunger used to be a term for that range where there was a deficiency but it wasn't obvious. If you put hidden hunger in a search engine now, you get all kinds of stuff about human micronutrient deficiencies. No one's talking about plants anymore. All right. Sometimes more than one nutrient is inadequate, so let's think about what happens then. You've probably heard of Liebig-Sprinkle law of the minimum or Liebig's law of the minimum. And what it says is that growth is limited by the growth factor present in the least adequate amount. All right? And yield is proportional to the most limiting factor. And a great example for that, and this example's been used since Liebig first talked about it, is the barrel stave example. And if you look at this picture here, you can see that if we assume that if every barrel stave was at the top of the barrel, things would be adequate, we can see that potassium is not quite up to the adequate range, nitrogen isn't up to the adequate range, nor is phosphorus. But what's limiting the growth in that case? The nitrogen, right? Because it's present in the least adequate amount, or in this case, it's got the lowest stave. Okay? Now, if you were to increase nitrogen up to the adequate level, would you get maximum yield? No, because you have two more things. And what would be next? The next limiting. Okay? If you go out into a situation and you think you've got more than one limiting factor and you try to guess which one it is, you could be right or wrong, depending upon what tool you use. And it'd be best to deal with all of them actually. And this is from one of the earlier pubs, and Liebig, of course, was German, so the first time these things were published, they were all in German. That's just a German barrel instead of an English language barrel. Because of the way nutrients interact in the soil, some of them are more mobile than others. That is, some of them are more prone to leaching than others. And if you were to add comparable amounts of these various nutrients to the soil surface and the same amount of rainfall were to occur, you would see that some things have leached rather far in the soil, whereas other things have not leached as far and other things have not leached at all. And the key to this is, does it interact with the soil? By interact, I mean, does it get taken up? Does it get absorbed by a reactive surface? Okay. You can see that nitrate doesn't get absorbed by a reactive surface compared to many of the cations, okay, or to phosphate. Phosphate is strongly attracted to things in the soil, iron oxides primarily. Most macros are strongly attracted to organic matter. They're going to tend to stay put, so to speak. Cations will move a little bit farther, but they'll be attracted to charged sites we'll talk about after lunch. And nitrate in particular is one of those little oxyanions that moves very quickly through soil. It actually moves a little bit more quickly than the water with which it exists. It's actually repelled by a significant volume of the soil, and it moves through a little faster. How do nutrients get from where they are in the soil to the plant? You know, plant roots are pretty extensive, but they're still not everywhere. These are the three mechanisms that are recognized: mass flow, diffusion, and root interception. Mass flow is the passive movement of nutrients with the soil water. Remember, the soil, the plants are taking up water, so there's a great potential, water potential, difference in water potential between the soil and the plant. There's a movement of water through the soil to the plant, and because there's nutrients dissolved in that water, nutrients are going to be delivered to the plant root interface with the water that the plant is going to take up. A lot of nutrients get delivered in that way. In some cases, diffusion is a major mechanism, and that simply means that the nutrients are moving from a region where they're in high concentration to a region where they're in low concentration. Well, the plant roots are taking up stuff, so there's a region of low concentration around the plant root. So there's going to be a tendency of things to move away from farther out in the soil to the vicinity of the plant root. And then finally, there's root interception, and that basically means that the root grew out to where the nutrient was. Big argument in the plant physiology literature right now as to whether this is significant or whether it was a mistake, but it sounds intuitive, so I'm keeping it. Okay. In terms of what nutrients get supplied in what mechanisms, here's a nice little table from a plant physiology book. Basically, it's estimating the amount of the nutrients of each nutrient that are delivered by either mass flow, diffusion, or root interception. And this is an interesting little table. You can see in the case of nitrogen that the vast majority of it is delivered to the plant roots via the mechanism of mass flow. That is, it's delivered in the water that's coming to the plant anyway. A much smaller amount is due to diffusion and very little to root interception. But contrast that with phosphorus, which exists in the soil solution in a much lower concentration. Plants still need a lot of it. So only 5% of the phosphorus that a crop needs is coming in through mass flow with the water that's moving to the plant anyway, and a huge proportion is coming through diffusion, which is the movement of a material from a region of high concentration to a region of low concentration. So this is just an interesting breakdown of how nutrients get, or what the dominant mechanisms are for nutrients to get from the soil to the plant. Okay, little practice question here. Examples of macronutrients are the following: A, nitrogen, iron, and potassium; B, phosphorus, nitrogen, and calcium; C, sulfur, nitrogen, and zinc; D, potassium, magnesium, and cobalt. Where are you going to throw your money, behind A, B, C, or D? A, okay. Do you agree? Does everybody agree with A? Does anybody agree with A? Are you awake? Okay. Okay. I'll tell you why I don't like A. It says macronutrients and it has iron. Okay? Iron's not a macronutrient. Could D be right? Cobalt's not a macronutrient. Cobalt's micro. C can't be right because zinc is a micro. Okay, so the only one possible here is B. Phosphorus, nitrogen, and calcium are all macronutrients. Okay, I want to talk a little bit about a soil model that will help us understand things a little bit better. That pie chart we looked at in the first section this morning is a nice beginning, but it doesn't begin to deal with as many of the issues as I think we need to understand in order to have some of these chemical concepts make sense to us. So we're going to expand our vocabulary and our concepts, and then towards the end we'll look at that two-dimensional slice of soil again. Okay, first of all, this is the soil model I like. I like it because I made it, but I mean it's a good model anyway, you know. Instead of just a big pie chart cut in half with a couple other slices, we now have a segment on the left that obviously has some similarity because these share a common wall, but it's divided into 3 parts. And I have a section over here on the right where I don't have them sharing a wall, so I think they're somewhat different from each other, but they're on this side of the diagram. And then I have this stuff in the middle. And what I'm trying to symbolize by these squiggly lines is that this line goes back and forth. Okay? And I've got a plant growing here. Okay? So does anyone want to hazard a guess, just a moment, of what any of these things are? A, B, C, D, F, or G? Yeah? No? Yes. So what? No, it's not related to soil horizons at all. Okay. Okay, well, here we are. Okay, I've got remember we had solids? Okay, I've got my organic solids over here, and biomass, residues, and byproducts, and humus. They're sharing a wall because there's so much of an intergrade between these two, you know. Sometimes it's hard, for example, to separate out these things. And then over here I've got my inorganic solids and my mineral solids. And I separated them out because there's a huge difference between primary and secondary minerals, and I don't want to mush them together. And then the stuff in the middle, of course, remember we said how dynamic the soil water is with the soil air? Okay, that's what we have here because, in fact, you can get pretty complete use of the soil solution during a droughty period, or the soil solution can take up most of this if we have a heavy rain. So this divider here just slides back and forth depending upon when the last rainfall event is and whether or not you have plants growing in that soil. Okay, so I want to talk between now and the time we eat lunch about how all these different pools, so to speak, interact and where there might be interactions. That is, where something in one of these boxes interacts with something in another one of these boxes. So let's take an example of biomass, for example. These are the living creatures that live in the soil. Do they interact with anything else that's up there? Do they take or give something? Think that's possible? Do they take? Of course, right? They need nutrients. They're going to take up nutrients from the soil solution into their bodies. Okay? We could call that microbial uptake if we're taking the position of the microbe, or we could call it a mobilization if we're taking the position we often take as crop managers. It's the same thing. They're going to take nutrients up out of the soil solution and use it for their own growth and metabolism. So there's definitely an arrow going from the soil solution to the biomass. Is there an arrow going back? Do microbes ever give anything back, exude anything? Of course. That's all those exudates we talked about. They release stuff into the soil. They release enzymes. That's how they break stuff down so they can take it up. So there's a variety of acids and enzymes and exudates, sticky exudates, whatever, that get released by the biomass back into the soil solution. Okay, so there's a two-way street there, so to speak. Okay? Now let's talk about humus. Does humus ever release stuff into the soil solution? Remember I said it broke down at a rate of about 1% a year? So if there's an arrow there, it's a pretty small arrow, okay, in terms of its release. Does it take stuff out of the soil solution? Well, it's not alive, is it? So it's not take it up the way microbes take up. But you notice I have a heavy line here? This represents reactive surfaces. It doesn't take up in the sense of absorb and tie up because it's dead already. But it does tie it up on its surfaces. Remember? It's small particles, it's highly reactive, has charge. So there is a lot of stuff that can be stored, so to speak, on these reactive surfaces. It can be absorbed onto reactive surfaces. So I wouldn't say that the soil solution goes into the humus because it's not alive, but I will say that it goes to the reactive surface out here. And that's what I'm trying to symbolize by this as opposed to this. Okay, let's go to this side for just a moment. Do primary minerals ever release anything into the soil solution? Do they interact at all with the soil solution that bathes them? Yeah. Quickly? It depends on where you are. Back here in the humid region, what we've got left in our soils is probably pretty worked over, so to speak. The stuff that's going to dissolve in large amounts or weather quickly is probably weathered away. But yes, they do contribute material to the soil solution, and we call that process weathering. It's the breaking down of minerals. Now, as a general rule, primary minerals in a humid, warm, humid region don't break down very fast, but they do break down. Now, if you were at a drier part of the country, warm and dry, there might still be some very reactive primary minerals that are weathering pretty quickly, but that's probably not the case here. So yeah, primary minerals do release materials into the soil solution, probably not rapidly enough to meet the crop needs if they're a macronutrient, however. For example, one of the materials labeled for organic growers is something called green sand. Okay? It's a primary mineral, and it contains potassium, but it doesn't weather very fast. Matter of fact, most studies indicate that it weathers extremely slowly, but people buy it and put it on for its potassium sources. Does stuff from the soil solution ever come back and form a new primary mineral? I.e., do you think there's a two-way street here? We know there's a street going to the left. Is there a street going to the right? Can primary minerals form in the soil solution? What do you think? How many people say yes? How many people say no? Most of you are saying nothing. Okay. Primary minerals are minerals that formed under conditions of a pretty high temperature and pressure. Okay? So we can't reform them from what's in the soil solution. New minerals might form in the soil solution. New minerals do form in the soil solution all the time, but they're not primary minerals. Primary minerals are a one-way street. If stuff gets dumped in there and it's a high enough concentration that a new mineral forms, secondary minerals. Okay? Primary minerals are minerals that form when magma is solidified. Secondary minerals form from the breakdown products of primary minerals or from other secondary minerals. Secondary minerals form in soils and sediments all the time. Okay, secondary minerals. Can they weather? We agreed, I believe, that primary minerals weather. Do secondary minerals weather? Sure, everything weathers. Everything that's alive gets older and dies, and everything that's inorganic weathers. Okay, so yeah, there'll be some weathering. For example, some clays, I'll talk to you about a whole suite of clays. Some clays are considered to be younger clays. They weather over time to the older clays. Okay, so yeah, secondary minerals weather. They can weather into their components into the soil solution. Now here, there's a two-way street. Because if the right concentration of ions exists in the soil solution, a new mineral can form. So in this case, you can get new secondary minerals forming out of materials from the soil solution. So this was a one-way street. This is a two-way street. In addition to that, I've got this little heavy line here. This indicates that the secondary minerals have reactive surfaces. So beyond weathering and formation of new minerals, we have this phenomenon of surface adsorption. stuff coming to a reactive charged surface and being held at the surface. Not in the mineral, at the surface. Yes? No, not at all. Not at all. Not related at all. Primary minerals and secondary minerals are not related to macros and microbes. Primary minerals are minerals that still exist in a soil or sediment. You can find them in creeks and water bodies too, that have not changed in their chemical composition since they were solidified from magma. They're probably much smaller in size now. If we're talking about them, they're sand, silt, or clay size. Whereas secondary minerals are minerals that form from the breakdown of primary minerals or the breakdown products of other secondary minerals. Okay, so I think we've established a one-way street here and a two-way street here, and then there's a second two-way street between the reactive surface and the soil solution, where stuff from the soil solution can get attached to a surface, or it can be kicked off by something else and be bounced back into the soil solution. We're going to call that exchange. Goes back and forth. Okay? So there's quite a bit going on over here. Let's talk a little bit more about here. We talked about the fact that the biomass takes stuff out of the soil solution and also gives stuff to it. Let's realize that the biomass relies upon this residue and byproducts for energy and nutrients. Okay, so they may exude byproducts and they may leave their residue when they die, but they're also consuming this as a nutrient and energy source. Right? Where does humus come in? Well, again, there's discussions, arguments about humus formation. It's probably the result of the polymerization or the building up together of stuff that was resistant to breakdown with perhaps some new molecular components built in. Okay? It's formed by biochemical activity. Is it a good nutrient source? No, but it's highly charged, it holds water, it holds cations, it's great stuff, you want enough there. Does the soil air affect any of these other things, do you think? Let's say that it rained heavily and the soil solution filled up most of the pores 2 weeks in the summertime. Is that good? No. Your crop's probably sitting out there covered with water, wilting, isn't it? Okay? But does it affect anything here? Suppose it affects any of your microbes? Yeah. A lot of them, just like roots, are aerobic. And if your soil stays flooded, especially when the weather's warm and things go anaerobic or inadequate amount of oxygen, they will suffer and perhaps die. So it can certainly shift your microbial populations temporarily. It can also affect your primary minerals. When there's not enough oxygen, things with iron and manganese are more soluble than when there is enough oxygen. So you can actually get both primary and secondary minerals becoming more soluble or more highly weatherable under waterlogged conditions where the oxygen is all used up. So we often take the plant grower's view here of soil solution and soil air, but in fact it does affect the solubility of some of your minerals, and it certainly affects the survivability of your creatures in your soil. Okay? Now the reason I like this diagram as opposed to the pie chart, I'm not opposed to the pie chart, it's a nice intro, but I like this because it allows us to put the arrows where they belong. And I won't show you where all the arrows are because it gives me a headache. But the fact is, there's a tremendous number of interactions between the pools as I try to show them in these little compartments. Any questions on this? Okay, I'm going to make one more point before I go on. Secondary minerals, these are what we often call in soils the clay minerals, as opposed to the clay size stuff, which we talked about before. These are called clay minerals. They usually are composed of layer silicates or platy minerals. They also are composed of our iron oxides. Now we have experience with them here. We have a lot of soils that have this reddish component, or reddish brown or reddish gold. That's due to one of the groups of secondary minerals, the oxides, primarily iron oxides in our climate. But the clay, the platy clay minerals and the secondary oxides are down in this pool, and we're going to talk a lot more about the characteristics they have in terms of charge after lunch. But before that, we're going to look at a graph that talks about surface area and reactivity. Remember I said this morning that soils are reactive, three-dimensional dynamic systems, and their reactivity is a function of the particle size they've got, materials they've got in their soil. And if you look at a number of both physical and chemical properties, surface area, this would be like how many square meters you have per gram of stuff. Swelling potential, does the material swell when water is added to it, or does it not change size? Absorption capacity, this is with a D, does it hold stuff at its surfaces? Does it hold water? Is it plastic? Okay. We see that there's not many of these properties demonstrated. There's not much surface area. There's no swelling potential. You don't get much absorption of water or nutrients with sand-sized particles. They don't have much surface area, and that's where these things happen because of surface area. But as your particle size decreases through the silt range, the clay, and then the very fine clays called colloidal clays, these are clays that stay in suspension and scatter light and do all that stuff colloids do, that the properties of surface area, swelling, absorption potential, water holding capacity just skyrocket. So when you talk about soils being reactive, in the mineral side of the story, it's the clay-sized particles that are the reactive ones. They're the ones that hold water. They're the ones that hold nutrients. Of course, they're also the ones that swell, and it's worse of a problem with some clays than others. But there are parts of the country where you've got to scrape away a certain amount of soil material before you build a bridge or build a house because it's a high shrink swell clay, and you can't put a foundation on it, you know. More of a problem out west than in areas where there's a kind of clay I'll point out when we go through our discussions today. Anybody ever had that experience? Anybody ever lived anywhere where you had to take special precautions to build because of shrink swell clay? What state were you in? Missouri, okay. Illinois, okay. I know my husband and I built a house on a slab in southern New Mexico back in the 70s, and they had to scrape about 3 feet away and put sand in there because the clay had a high shrink swell. So it's an adaptation many people have to make. Okay, we're back to our two-dimensional model again, which I think is helpful. And let's look down here and see what some of these things are. First of all, you know water. We've got water films around particles. Every particle's got a water film. It might be pretty thin, but it's water film. Some pores are filled with water. Some are filled with air. So this would be a macropore, and it's drained. Okay. A lot of big particles, the sand and the clay, the sand and the silt-sized stuff, are often said to make up the matrix of the soil. And then other things are wrapped around it or in between it. One thing you notice, clay complexes, these little books, stacks of things. Let's find one. I think these are all them. Clays tend to exist in stacks of plates. They're talking about the aluminosilicates. And so this soil doesn't have a whole lot of clay, but where it has it, it's in a little stack or a clump or a cluster. Also realize that you've got places where microbes live and they're protected. You know, like this is a safe place for these little guys to live because look who's out here looking for food. Okay. Some microbiologists now believe that about 90% of the biological activity in soil occurs in about 10% of the volume, and they exist. They tend to exist, number one, where there's food, and number two, where it's safe from predation. Okay, remember, we've got food webs going on down here, and this creature here is looking for something to eat. You've also got roots, and see how we've got things living on the roots. Remember I said there's a lot of root exudates, there's a lot of carbon compounds given off, and the rhizosphere, that zone right outside the root, is so rich in easily metabolizable compounds that you tend to get a lot of creatures living there. Now in this case they're showing an amoeba. The amoeba is there because she's grazing on the bacteria. The grazers, they're actually grazing on the bacteria that are living on the root because it has so much good stuff to eat. Okay? In this case, we've got this fungus hyphae growing in here. The biomass itself can, in the case of fungus, can wrap around particles and hold them together too. So there's a very rich biological and ecological environment in this little soil here.